Hi, everyone. So far this semester, we've been focused pretty much solely on finding and evaluating limits of functions of several variables, whether those were scalar fields or vector fields. And then in the previous video, we looked briefly at how a lot of things about limits and continuity really are very similar to what we saw in Math 5610. So today, we want to start thinking about how we might think about something like a derivative for either scalar or vector fields. Now, we're actually going to begin by thinking about scalar fields for reasons that will hopefully become apparent in a few moments. We'll start with scalar fields. We'll try to make sense of what the derivative of a scalar field at a particular point in the domain might mean. And we will start trying to calculate some of those. Now, like many things in mathematics, this is going to be an iterative process. So we will define something, we'll decide that it encapsulates some, but maybe not all of what we would like, and we'll move on from there, right? We'll modify that definition slightly. We'll make some additional restrictions. But we want to start today by simply recalling, right, what was the definition of the derivative for a function from R to R. So right back in 5610, or indeed, you've probably seen this definition as far back as Calc 1, right? You define the derivative of a function f at a point A to be equal to, now there are usually a couple of types of limit definitions that might float around. The one I want to focus on is this one, the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay, so this is exactly or equivalent to whatever definition of limit you would have learned in a Calc 1 course and you've worked with lots. And then in analysis, right, we start to prove things using this limit definition to be the definition of the derivative. So what we want to think about is, okay, this worked assuming A was a point of my domain, right? What about, right, what if now I'm imagining f is a function from some subset S of Rn into R. Now you might say, okay, why are we not doing Rm here? Well, let's actually stop and think about what that would what issues that might cause for a second. So if I were to take so a function from Rn to Rm, right? Then this is going to be a vector quantity. This will be a vector quantity. I could take that difference, except, well, what is h? I've got to deal with that. Is h a vector or a scalar? If this is a vector, if h is a vector, I'm okay up here, except dividing by a vector won't necessarily make sense. So maybe it's a scalar, but if it's a scalar, this isn't going to make sense. So there's going to be problems, and some of it's going to be a problem whether I'm from Rn to Rm or from Rn to R. The reason we're really going to start with R is because notice that that keeps this expression as, if this is mapping into R, this is still a scalar expression, right? So the thing I'm going to get out is going to be a number, right? I'm going to get out some real number. So let's start there. We will eventually, of course, work our way up to describing derivatives of vector fields. But it's sort of nice to start with the simplest possible case where as little as possible changes, right? So I already know how this works if f maps from some subset of R into R. So now what I'm really changing is this piece, right? And I'm just changing the dimension of the domain. Let's keep the dimension of the range fixed. Later on, right, we can come back and say, okay, what happens if I'm mapping from some subset of Rn into Rm? Now, as we go along, you may see naturally, how we might fix some of this, but we'll come back to that in a bit. It actually turns out once we deal with this case, we'll be able to shortcut some things about the more general case. All right. So let's think about this. If we're looking at Rn, a function f from some subset of Rn into R, what are we going to need to, what's not going to work about this definition, right? What about this limit am I going to have a problem with definitionally? So actually what I would encourage you to do is pause the video, think through which of these things will be defined and what might be problematic, uh, given that we have a function now from a subset of Rn into R. So if I look at this expression, the first thing I notice is that I'm going to have a problem here, right? So here I have A plus H, but I'm now imagining, right, this A should be something in my domain, right? So A, I'm imagining, is going to be a vector in Rn. So the question becomes then, well, what to do with H? Okay, so one solution would be, well, H should be a vector in Rn also. But if I do that, then I'm going to have up here a scalar quantity divided by a vector quantity. That doesn't really make any sense, and I don't really know a good way to even start to make sense of that. So I say, well, I don't really want, I don't, this has to be a vector, but this can't just be a scalar. This thing sitting here can't just be a scalar. So I'm going to need to fix this. Now, let's back up for a second to figure out how to fix this. Let's back up and think about what was the point of having A plus H here at all? Well, in the single variable case, right? The idea was you have some function. Okay, so here's my function f, right? You want to calculate the derivative at some point A, and A plus H was some point close but not equal to A, right? Now, as we think about what's going to happen as we move up a dimension, well, the problem is as I move up a dimension, okay, so now imagine here's my point, here's my point A, but now A is a vector, right? It has X and a Y coordinate, right? So this is my vector A. If I want to define a point that is close to but not equal to A, I can't do that just by using the scalar distance. So here, right, H, if H was positive, that immediately defined the point A plus H, which was to the right of A. And if H was negative, then A plus H defined a point that was to the left of A. The problem I have here is that a scalar is not enough to define a unique point. I can't just go, if I go distance h away from A, I actually get like a circle's worth of points. So I need to define this point by giving some vector, actually, right? And then what I want is I want that point to get closer and closer. So what I need to do is I need to define h times sort of some direction vector here, right? I need a vector to give me the direction. Okay. Now that's going to be different, right? I'm going to get different things whether I take a derivative with respect to this vector or this vector or this vector over here or some other vector out here, right? So I really this A plus H, I want the thing that I'm adding to A to be going to the zero vector, but I need to add in some vector direction here. So what I'm going to do is I'm actually going to come up here and I'm going to replace this A plus H with an A plus H times Y. Now again, my answer then is going to depend on what Y I choose. And so therefore what I'm doing is I'm not calculating, there is no single derivative of f at A, at least not using this notion. There's no single derivative of f at A. However, there is a derivative of f at A with respect to whatever y vector I choose here. Okay. So what we want to do is we want to define the derivative of f with respect to a vector y and at a particular point A. So again, a derivative is still a local quantity, right? It's telling us something about our function at a particular point A, but now we have to specify what we are taking the derivative with respect to. Now, you may be thinking back to Calc 3 and thinking like, oh, wait, this sounds sort of maybe like is there some connection to a partial derivative or directional derivatives or something? There is a relationship, but they are not equivalent. And we will get to that, not totally in this video, but certainly in the next video. So let's look at this definition first. So I want to define the derivative of a scalar field with respect to a particular vector. So let f be a function from some subset of Rn into R. That's a scalar field. And let A in our domain S be an interior point of S. Then let Y be any fixed vector in Rn so that we can define the derivative of f at A with respect to Y so we're going to use this notation here. Again, it's like f prime of A, but now we also further need to specify what vector we're taking a derivative with respect to. So we would say this is the derivative of f at A with respect to Y. And we're going to define that to be the limit as h goes to 0. Now, again, this is just a scalar limit, right? So the limit as h goes to 0 of f of A plus hy minus f of A divided by h, if that limit exists. So if the limit exists, then we say the derivative of f at A with respect to y is just whatever the value of that limit is. Now, there is one other small detail we want to check, and actually the definition here helps us make sure this is okay. I'm assuming that A is in my domain S. So f of A will certainly be defined. How do I know that f of A plus hy is defined, right? Because just because A is in the domain does not necessarily mean that A plus hy will be in the domain. Well, this is where we actually need this additional condition that A needs to be an interior point of S. So imagine, right, I have over here some set S. This is the domain of my function. So actually some definitions will just define S to be an open set, in which case, if S is an open set, every point is an interior point. But we don't make that restriction. So S could be any set, A just needs to be an interior point of that set. So what does it mean for A to be an interior point of this set? Well, it means that I can find some ball, right, centered at A, such that this open ball lives entirely inside S. Now, why is that helpful? Well, this is my vector A. Now imagine I'm taking a derivative with respect to some other vector y, and let's imagine y points out this way. Well, if this vector is y, okay, then for example, A plus y would be this point out here. That's not in S. So f of A plus y is not in the domain. So that doesn't make any sense. But notice I'm taking a limit as h goes to 0, and I'm looking at A plus hy. And so what's going to happen is hy is getting smaller and smaller and smaller. Because A is an interior point, eventually this is going to scale down such that eventually A plus hy, so this here is just hy. The point out here would be the vector A plus hy. But eventually A plus hy will be entirely inside this ball, and because this is an interior point, that ball is entirely inside S. So because A is an interior point, I know that there will be some value of h, some positive value of h, below which all other values A plus hy will be in the domain of S. So this interior point condition essentially makes sure that this will be well defined for all h sufficiently close to 0. So this definition is well defined, and we can actually use it to start calculating some derivatives. So what I want to finish this video with is just working through a couple of examples to see how this works. And if you think back to Calc 1, what's sort of the first example you want to do? Well, you probably want to look at like a linear function, right? Like, so when you were just taking derivatives of functions from R to R, using the limit definition, maybe in a Calc 1 course, right? You probably looked at something like, f of x is equal to, 3x or 3x plus 1 or something. Well, let's use here linear functions, okay, as our first example. So let's suppose that we have a function f which maps from Rn into R, which is linear. Okay. Now, let's first, what does it mean for a function from Rn to R? What does it mean for it to be linear? Well, it means that f of x plus y is equal to f of x plus f of y for all x, y in the domain. And it also means that f of any constant times x is equal to c times f of x for all x in Rn and for all constants c. Okay, so assuming that's true, so assuming we're dealing with a function of this type, what could we say? Well, let's see. So if I wanted to calculate the derivative of this function at some point a with respect to y, right? By definition, that would be the limit as h goes to 0 of f of a plus hy minus f of a all over h. But now I can use my linearity conditions here. I can break this up over the sum because f is linear, and I can pull this scalar h out. So this becomes the limit as h goes to 0 of f of a plus h times f of y minus f of a over h. And you quickly notice, I have a f of a minus an f of a. Now I have an hf of y over h, and the h's cancel, and I'm just left with a limit as h goes to 0 of f of y, which is now, this is a scalar quantity, which is independent of h. So this value is just f of y. And so what we see here, right, is that if I have any linear function, its derivative actually is just calculated by evaluating, its derivative with respect to a particular variable y, or a particular vector y, can be found by just plugging that vector y into the linear function. Notice in particular, it does not depend on a, right? And if you think about it, this sort of makes sense. If I think about the function 2x, right, f of x is equal to 2x, its derivative is 2. That value 2 does not depend on what point I'm at in my domain. This derivative is independent of the value in your domain. Okay? All it depends on here is what you're taking a derivative with respect to. Right? If you're taking a derivative with respect to y1 versus y2, you'll get a different answer, but it's going to be fixed for every point in the domain. All right. So, linear functions, not surprisingly, right? Everything works out really nice. Let's deal with something that's a little slightly more complicated. Of course, we could make these arbitrarily bad, right? By adding in lots of complex functions. We really want to focus on the key sort of fundamental examples, though, to build some intuition for using this definition. And then, of course, we'll later on build a few more tools which allow us to understand some of these quantities without having to go through all the tedium of using the limit definition. All right. So let's see, what would you normally do after linear, right? Well, if you're thinking about functions from R to R, you might do something quadratic. So let's do something sort of quadratic. Let's think about the function f of x is equal to the norm of x squared. Now, if you think about this, right, if instead of thinking about this in vector terms, you just thought about this having three scalar inputs. So imagine this is say from R3 into R, right? So you could think about here are my three scalar inputs, right? And right, the norm of this vector with components x, y, and z, or sorry, rather the norm squared would just be x squared plus y squared plus z squared. So really this is exactly like some sort of quadratic thing. If you just do R2 from R2 into R, you would get this. And if you were to graph this in R3, right, you just get this surface, which we call a paraboloid, right? It's like a parabola, but just rotated around the z-axis. So this really is sort of the of functions from Rn into R. This is the simplest sort of quadratic thing you might get. So let's see if we can compute a derivative here with respect to an arbitrary vector y. All right. So let's start by just first writing out, what is the limit definition? Okay. So if I wanted to compute f prime the derivative of f at a with respect to y, the limit as h goes to 0 of f of a plus hy minus f of a over h. Okay. Now in this case, let's see, what is this? This is the limit as h goes to 0 of the norm of a plus hy squared minus the norm of a squared divided by h. Okay. Now, you've done enough limit definition of derivative type stuff, right? I need to simplify this somehow. And often, right, it's not this that needs simplifying, it's this, right? Hopefully this is going to cancel out with something over here later. So I need to figure out some way to re-express this. And the thing I always think of anytime I see a norm squared, I remind myself, the norm squared, the norm of a plus hy squared, that is the same as the inner product of a plus hy with itself. Now, this inner product, much like a regular product, right? I can distribute here. Now, again, this is we're really thinking about the dot product here, right? So I can distribute this. This will be the same as a inner product with a plus 2 inner product of a with hy plus inner product of hy with inner product of hy. Okay. Now, inner product of a with itself, that's just the norm of a squared. Okay. Here, I can pull scalars out of an inner product. So this is a 2h inner product of a with y. Okay. And now this last thing, I can pull an h out of each term here. So that's going to give me an h squared. And then I'll be left with an inner product of y with itself. That's the norm of y squared. Okay. So I now have a nicer expression that I can plug in here. So now this becomes the limit as h goes to 0 of, so this first piece now becomes norm of a squared plus 2h times the inner product of a with y plus the norm, or plus h squared times the norm of y squared. And then we still have this, right, minus norm of a squared all divided by h. So now, a little bit of algebra, right? We've got Norm of a squared minus the norm of a squared. Each of these has a factor of h that I can factor out and cancel with this. Okay. And so what I am left with is, this is the limit as h goes to 0 of 2 times the inner product of a with y plus h times the norm of y squared. So remember, y is a fixed vector, right? As far as we're concerned, a right now is also a fixed vector. The only thing that's changing is h here. So this is a fixed quantity, norm of y squared. H is going to 0. This term is going to go to 0. This is independent of h. And so we get that this is 2 times the inner product of a with y. So let's solidify this a little bit let's actually plug in some particular values of a and y. So given this formula that we've now proven, right, I could come over here and, I could imagine, okay, let's let a be a fixed vector, say 1, -2. And then let's let y1, we're going to look at 2 different y values. Let's let y1 be the vector -3, -36. So if I do that, then the derivative of f at a with respect to y1 will be equal to, well, it's just going to be 2 times the inner product of a with y1. Okay. Well, what's the inner product of these two things? So first components multiply together to give me -3. These multiply together to give me -12. -3 plus -12 is -15. So I get 2 times -15, which is -30. Okay. But what if I took another vector? So what if I took y2, let's say, to just be -1, 2? Okay. Well, then f prime of a y2 would be 2 times the inner product of a with y2. The inner product of a with y2 would be what? -1 plus -4. That would be -5. It would be 2 times -5, which is -10. Okay. So great, right? We can calculate these things. But now the question becomes, what does this mean, right? What does this number tell you? Now, we would like for derivatives to tell us something about like a rate of change, right? But immediately the question I'm confronted with, if I look at these 2 vectors, y1 and y2, right? These are not unrelated vectors. In fact, y1 is 3 times y2, right? So these are scalar multiples of one another. And so what we notice is that even though these are in the same direction, right? These vectors point in the same direction. This one just has a magnitude that's 3 times the magnitude of y2. What we notice is even though they're in the same direction, we get different values for the derivative. So the derivative here can't be just like purely a directional derivative, because you would imagine that a directional derivative would only depend on the direction, not the magnitude of the direction you're going in. So somehow this is not quite a directional derivative. This really is a derivative with respect to a vector, because it depends on both the magnitude and the direction of this vector. So what you get out, right, depends on the magnitude and the direction of these vectors. These vectors are both in the same direction but have different magnitude. Therefore, we ended up with different answers here. Okay. Now, notice that, again, this vector is 3 times the magnitude of this vector. And notice that the derivative here is 3 times the magnitude of this. That is, in fact, true in general. You can actually make a slight adjustment here. Or you can play around with the limit definition to show that if you scale the vector y by some constant, that affects the derivative by scaling by that constant. But this is not purely based on the direction. It's based on both the direction and the magnitude of this derivative. So that's fine, but somehow that's probably not what we really want to work with most of the time. When we think about the things we used in Calc 3, like partial derivatives or directional derivatives, those only depended on the direction, right? Either the direction via, you're thinking about a partial derivative, so you're just moving in one of the, in either the x, the y, or the z direction, right? In the direction of one of the standard basis vectors, essentially. Or you're thinking about a directional derivative where the derivative only depended on what direction you were moving, not on anything to do with the magnitude going in that direction. So we want to figure out how to relate this back to something like that, right? And that's from a physical perspective, right? That's often what we want to do. We want to sort of make decisions based on a rate of change going in a specific direction. This is not exactly giving us that, right? Again, this is fully a derivative with respect to a vector where it does depend on both the magnitude and the direction of that vector. So moving forward, we'll need to modify this definition somewhat in order to encapsulate those kinds of physical properties that, well, physicists obviously care about, but also will be important to making some calculations, I think, a little bit easier as we move forward. So we will conclude this video here. And in the next video, we will see how this notion of a derivative of a scalar field with respect to a vector ties into notions of directional derivatives and partial derivatives.